Swayam Prabha. Digital India. Educated India.
Hello. So we will continue with proof techniques. Today I will introduce some proof technique which does not exactly come under the purview of first order or even propositional or predicate logic. This is something a little bit new. It requires a new assumption and we will start with that. So basically what we want to do today is proof by induction or inductive proofs, to be more precise. Now, before I proceed further, let me introduce some notations. N by the set of natural numbers, or this is another notation, Z plus, or we can even write more explicitly this as Z greater than 0 is the set of all integers N in Z, but only restrict to positive integers N greater than 0, that is N greater than or equal to 1. Similarly, we may think of sets like this: Q plus set of all positive rational numbers and set R plus the set of all positive real numbers. It turns out that the Z plus has a particular property which is not exhibited by this Q plus or R plus. This property makes this set somewhat distinct or different from this and this. So, in other words, Z plus is what is called can be well ordered. So, I now mention what this means. The well ordering principle. Now, this is something that does not immediately follow, actually does not follow from predicate logic or propositional logic. So, we assume this as an independent axiom. Okay. Difficult to prove this, although the statement you can just see that it's obvious. So, this says that let S be a subset of Z plus, which is not empty. Then the principle says that when S contains a smallest element. We cannot prove this independently, but we will show that this principle will lead to a proof of the principle of mathematical induction, and if we also start with the assumption that this principle of mathematical induction is an axiom, we can deduce this well ordering principle. Okay, on the other hand, so this basically says that Z plus is well ordered. On the other hand, if you look at this Q plus and R plus, they are not well ordered. For example, I can consider this. over n, for all n z plus. This is a subset of both q plus and r plus, right? But this does not have the smallest element. And this is definitely a non-empty set. In fact, it's an infinite set. Despite that, you cannot identify an n for which 1 by n is the smallest element, because 1 by n plus 1 is even smaller than that. Okay, so this proves that q plus r plus are not well ordered. Okay, so well ordering is not a very default property, but z plus satisfies this. Okay, and in fact, if I consider this, so z plus is 1, 2, 3, 4, 5, a set of natural numbers. I also often use this notation n0, 0, 1, 2, 3. I just add 0 to the set of natural numbers. So n0 is also well ordered. Okay, the same by itself. If I take any non-empty subset S of n0, then S contains the smallest or minimum element. Okay, so now let us see why it matters. Okay, so I now state the principle of mathematical induction. There are many forms. Today we will deal with principle of mathematical induction. Today we will use only the so-called weak form. Okay. So this goes like this. Let Sn be a statement about a positive integer n in z plus, okay, such that we have the following two conditions hold. One, S1 is true. So if I put n equal to 1, this is true. 2, Sn equal to true is true, implies Sn plus 1 is true for all n in z plus. Then the principle of mathematical induction says that Sn is true for all n in z plus. So in order to prove this, maybe I use another ink proof. So I will derive this principle of mathematical induction from the principle of well ordering of z plus. Okay. So suppose that maybe I use not S, A is a subset of Z plus such that S of n is not true whenever n is in A. I should have written it in a little better way. A is the set of all n in A for which Sn is not true. Okay. So, I prove by contradiction, I assume that A is non-empty. Okay. If A is non-empty, then I can pick some element n from A. Okay. Now it is given that S of 1 is true. So n cannot be 1. That is n greater than 1 by condition 1. Right. This essentially implies that n is greater than or equal to 2, that is n minus 1 is again a member of Z plus. I see. Okay, my choice of n is a little bit not, it's just pick n in A such that S is the smallest element of A. Okay, by Euler ordering principle, there exists an n. Not only it is empty, now if it is non-empty, I can always find this minimum element in A. And that follows from Euler ordering. Okay. Now, n is greater than 1 because S1 is true. Therefore, we cannot have n equal to 1. Therefore, n is greater than or equal to 2, and in particular, n minus 1 is once again a natural number, greater than or equal to 1. But by our choice of n, it is the smallest element of A. Therefore, n minus 1 in particular does not belong to A. Okay. So, by choice of n minus 1 is not in A, which means Sn minus 1 is true. But then, by this condition 2, we have n minus 1 plus 1, or rather S of n minus 1 plus 1, that is Sn, is true. But this is a contradiction to the fact that n belongs to A, and A comprises all those elements for which Sn is not true. So this is already a contradiction. So it says that our initial assumption A not equal to empty is false. It is not the correct assumption. So A is empty, which essentially implies that Sn is true for all n Z plus. Okay. So if I assume the principle of Euler ordering of Z plus, then the principle of mathematical induction follows, and I will give you a brief idea that the converse is also true. That is, the principle of induction implies Euler ordering. So we work out the detailed proof. So assume that the principle of induction holds, and I show that every element S, every set S or A contained in Z plus must contain a minimum element. Okay. So let us say this is a non-empty set in Z plus. I have to show that A must contain a smallest element or a minimum element. Suppose not. Okay. So, but then I can construct a sequence of elements of A as follows. I start with some n0. Anyway, it is non-empty, therefore I can find and n0 from A. Right. Now, since A does not contain the smallest element, n0 is not a smallest element in A. So, it contains some n1 in A, n1 less than n0. Again, n1 is, by this assumption, not a smallest element. So, I can compute or find an element n2 in A, which is smaller than n1. In general, I can, by induction, I can get any number of elements as that nk. I can do this till infinity. Okay, because no element n0, n1, n2, n3 will be there. Neither is the smallest element, so I can find even a smaller element and smaller element. Now by induction you show that nk is less than equal to n0 minus k. Because there are discrete jumps, right? n1 is n0 minus 1, n2 is at most n1 minus 1, that is n0 minus 2, and so on. But then if I put k equal to or greater than equal to n0, we will see that the kth element that I can choose from A under this assumption is either 0 or negative. But A is a subset of Z plus, which is impossible. Okay. So this once again provides a contradiction and proves that any non-empty subset A must have a smallest element. Okay. Fine. So that's basically the two-way proof. Induction implies well ordering and well ordering implies induction. Unfortunately, we have to take either induction or well ordering, which are equivalent essentially, as an axiom. There is no way to prove these things independently. It seems like true. It is very difficult to find counterexample. It is impossible to find counterexample. So we just assume, we start our mathematics with the assumption that this is true. Okay. Now I can slightly generalize the principle of mathematical induction this way. So let Sn be as a statement about positive integer n greater than or equal to n0, and I have these two conditions. As n0 is true and for all n greater than or equal to n0, Sn is true implies Sn plus 1 is true. So earlier we have started our induction with n0 equal to 1, but I can start from anywhere else. Okay, I can start from 0, I can start from 2, I can start from 5, and so on. Then Sn is true for all n greater than or equal to n0. Whatever happens before n0, that is not my concern in this statement. So earlier we had n0 equal to 1, but we may have n0 equal to 0, n0 equal to 2, n0 equal to 4, 100, all the things are possible. Okay, this is a slight generalization of the previous statement. Okay, so now let us see how the assumption of this either well ordering or the principle of induction allows us to prove a lot of interesting theorems about integers. Okay, so I will give you a series of examples one after another to demonstrate how things work, how such proof techniques can be very useful to us. Maybe I start with example 1, a very easy one. So for all n greater than or equal to 0, we have 1 plus 2 plus 3 up to n equal to n plus 1 by 2. Okay. So how do I prove it? So this is a case of induction, and this here n0 is 0. So there is a basis step, induction basis, and there is an inductive step. So basis is n equal to 0. If n equal to 0, this is an empty sum, right? So empty sum always evaluates to 0, right? Whereas the right hand side I have 0 times 1 by 2, which is also 0. So 0 equal to 0, no problem. So the induction basis holds. Now the induction step. Of course, you could start the induction from n equal to 1 itself. So this side is 1, this side is 1 times 2 by 2, that is 1. It's okay. I am starting from n equal to 0 to highlight whenever you have an empty sum, it is 0. And whenever you have an empty product, it is 1. Okay. Because this is how to, remember this. If you are asked to write a program to implement this sum, then you start initializing a sum at 0. Then you, in a loop, you add 1, then 2, then 3, then 4, and so on. Likewise, if you want to compute with n factorial, 1 times 2, you initialize your product to 1. Then you multiply 1, multiply 2, multiply 3, and so on. Okay, anyway. So empty sum is 0 always. Remember this. Now what is the inductive step? Suppose that this is true for sum n greater than or equal to 0. Then I have to show that this is true also for n plus 1. This will be n times n plus 1 by 2 plus n plus 1. You can take n plus 1 common, and after a little bit of algebraic manipulation, so what will be n by 2 plus 1? So we will have n plus 1, n plus 2 by 2, and this is nothing but n plus 1, n plus 1 plus 1 whole by 2. So this step is called the induction basis. Both are very important, and this step is called the inductive step. So we assume something for a particular value of n and prove it for the next value of n. Anyway, I believe we have already seen examples or proof examples like this. So it has move on. This is example 2, but this is not an example of induction. It is just an application of the previous formula. I just mentioned this because it's a very interesting application. Okay. So what happens is like this. Okay, maybe I draw a circle. Where is that thing? Here, I believe. No, not select. Draw a circle. Okay, good. Okay. Suppose this is a circle, and then maybe I just go back to this, otherwise it will keep on drawing circles. Oops. Not a good thing, not a good thing. Let me... Why cannot I choose this? This is very... something wrong. I cannot choose all the things. Let me see if I can. Some problem. Not select. Why is this not working? Okay, so there's a problem, I believe. Oh, I see. It's understood. Let me see if it works. Okay, so we have 1. Okay, I also will go to the full screen mode. 2, 3. These numbers we write somewhere up to 36. Okay, in some haphazard random fashion. Then maybe I call this x1, x2, x3 up to, and so on. Eventually you come to x36. The idea is that I can always find 3 consecutive numbers. So there are always 3 consecutive numbers on this. xi plus 1, xi plus 2. Of course, whenever I call I plus or I plus 2, I always think about if it is 36, then the next one is not 37, 38, but 1, 2. If it is 35, 35, 36, 1. Otherwise, if it is something like 18, 18, 19, 20. Okay. 3 consecutive numbers, this must exist. Such that their sum is greater than or equal to 55. Okay. So I assume that this is not the case. So this is a proof by contradiction. So I will assume that x1 plus x2 plus x3 less than 55. x2 plus x3 plus x4 less than 55, and so on. Eventually I have x36 plus x1 plus x3 less than, x2 less than 55. Now if I add all these things up, I see that x1, x2, x36, here x1, x2, x3, the previous one will be x36, and here I am starting from x2, this will be x1, x1, x2, x3, x4, x36. So this is 3 times the sum of x1 through x36, but x1 through x36 is nothing but a permutation of 1, 2, 3 up to 36. So 3 times 1 plus 2 plus 3 plus ... 36 is less than 36 times 55. Okay. So then if I use that formula, 3 times, this is 36 times 37 by 2. 36 times 36 plus 1 by 2. This is less than 36 times 55. So cancel 36 here and 36 here, positive thing you can cancel, and multiply by 2, 3 by 37, 3 times 37 will be 111 less than 110. This is absurd, right? So this is a contradiction which proves that I can always find 3 consecutive integers here. The sum is greater than or equal to 55. Okay, but this is not an inductive proof. It is just a proof by contradiction using the earlier result. Because this is very interesting, I just covered this. Okay, so let us look at some other proofs. What is the next proof? Okay, this is a very important thing. Yeah. let me first state the example 3, I believe this is. For all n integer greater than equal to 0, n is less than 2 power n. Okay, this has a very big implication later, we will see. If we have a set of size n, then the power set of that set has size 2 power n. This example actually establishes that the size of any set is strictly smaller than the size of its power set. Okay. In fact, later we will generally prove that this is true even for infinite sets. But please hold on. Those things we will study a little later. But for finite sets, I can give a very simple and simple and elegant proof based upon induction. So this is, I can start with n equal to 0. Actually, I should start with, because this assertion should also hold for the empty set. When I have 0 less than 1, which is 2 power 0. Okay. On the other hand, in order to complete the proof, I have to propose the inductive step. Okay. Suppose n is less than 2 power n for some n greater than equal to 0. If n is greater than equal to 0, 2 power n is greater than equal to 2 power 0, which is 1. So I can write 1 less than equal to 2 power n. Now if I add them up, this is a less than equal sign, and this is a less than sign. Now if I add, it will be less than sign, n plus 1 less than 2 power n plus 2 power n equal to 2 power n plus 1. So this completes the inductive step. Okay, so once again it's a very simple inductive proof, but it will lead to a very important, I would say, conclusion. Finite sets are strictly smaller than their respective power sets. We will prove this also for infinite sets. Actually, our proof will hold for any set, if finite or infinite. But that will come little later down the course. Okay, then what is it? Example 4, maybe this is a good thing. This is another good thing. Although not that difficult, but this is an interesting thing. Okay, so you know harmonic numbers, right? So harmonic numbers are defined as Hn equal to 1 over 1 plus 1 over 2 plus 1 over 3 up to 1 over n. And this is defined, let's say, for n greater than equal to 1. Again, if you consider n equal to 0, this is an empty sum, so that can be taken as 0. But let us for the moment define it for n greater than equal to 1. So these are my harmonic numbers. So the statement that we want to prove is for all n greater than equal to 1, h1 plus h2 plus hn is equal to n plus 1 hn minus n. Am I correct? Yes. H1 plus h2 hn is n plus 1 hn minus n. Okay, fine. So how do I prove this? Again, you know, this is an inductive proof. Basis, take n equal to 1, left hand side is h1, which is 1, and right hand side is 1 plus 1, h1 is 1 minus 1, that is 1. Right? This is 1 plus 1, h1 is 1 minus 1, that is 2 minus 1, that is 1. And in the inductive step, we assume that this is true for some n greater than or equal to 1, then I will prove it for n plus 1. Then h1 plus h2 plus hn, just add another hn plus 1. By induction, this sum is this quantity. So I have n plus 1 hn minus n plus hn plus 1. Right. Okay. So now I use this formula n plus 1 hn. Okay, maybe I do this. hn plus 1 minus 1 over n plus 1 minus n plus hn plus 1. Okay. So hn is hn plus 1 minus 1 over n plus 1. So now if I club together all these occurrences of hn plus 1, I will get n plus 2. Here I have n plus 1 is n plus 1, and here I have another occurrence. So n plus 2 hn plus 1. This n plus 1 and this n plus 1 will cancel. Cancel multiplicatively. Minus 1 giving minus 1, so minus n plus 1. So this is nothing but n plus 1 h n plus 1 minus n plus 1. Okay. Okay, so we will take up the case of harmonic numbers from time to time. There is another interesting series that you should be already aware of. So these are called Fibonacci numbers. And let us prove some assumption, some statement about Fibonacci numbers using induction. So Fibonacci numbers are defined recursively this way. Okay, this is something. F0 is 0, F1 is 1. Subsequently, Fn is the sum of the previous two terms in the sequence. This is for all n greater than or equal to 2. Okay. So now what I will prove for all n greater than or equal to maybe 0, 1, it doesn't really matter, but maybe okay, maybe 0. F0 square, F1 square, F2 square. Well, okay, fine, no problem. Sum goes up to Fn square. This is equal to Fn plus 1. Okay. So how do I prove it? Again, fairly straightforward, this proof. First the basis case. Take n equal to 0. Then LHS is F0 square, 0 square, which is 0. And RHS is F0, F1, which is 0 times 1, which is 0. So equality holds. In the inductive step, we assume that this holds for some n greater than or equal to 0. Then I have to show that this is true for n plus 1. Then this is just an additive addition, a new term. Therefore, this quantity is equal to this quantity, so I write it like this, fn plus 1. Then I have added the new term, fn plus 1 whole square. Then I can take fn plus 1 common, and then I have fn plus 1. By definition, this is fn plus 1, fn plus 2. And n plus 2 is nothing but n plus 1 plus 1. So I am not writing it. Okay. Okay. So this is another interesting example. All these are, I believe, somewhat, what would I say, easy proofs. Let us now look at a slightly more complicated proof. Okay. So just recall. Ordered we have already covered this in some other context. So this means in how many ways you can write, for example, if I take n equal to 4 as a sum of positive summands. 4, for example, can be written as just like 4, 3 plus 1, 1 plus 3, 2 plus 2, 2 summands, 3 summands, and because this is ordered, this and this are considered different. And if I consider 3 summands, 1 plus 1 plus 2, 1 plus 2 plus 1, 2 plus 1 plus 1. And finally, if I have 4 summands, we have this. So 1, 2, 3, 4, 5, 6, 7, 8. Using some logic, we have proved that the total number of compositions, ordered compositions for n in n is 2 power n minus 1. Right, we have proved it. So I will now give an inductive proof for this. So this is true for all n greater than or equal to 1. Okay. So induction basis. N equal to 1. Of course, there is only one way of writing 1, that is like this, 1 equal to 1. And so, this count is 1. On the other hand, 2 power 1 minus 1 is 2 power 0, which is also 1. Okay. So, for the inductive step, I do something in this. First, I identify those compositions where the last summand is larger than 1. So it is one such thing, this is one such thing, this is another such thing, and this is another such thing. In other cases, I have the last summand is 1. Okay. So now, suppose that, okay, so I assume that n has okay. So I want to now count the number of number of ordered compositions of n plus 1. So what I do, I start with a composition of n. So n plus 1 is 4, n equal to 3. Okay. N minus 1 is 3. Okay. So 3 has, okay, how do I write in this page? It is getting full. Let us do this thing. Let us open another page. So I will illustrate this process for n equal to 3. And you can easily, I would say, generalize this to other values of n. Okay, 1 plus 1 maybe 3 sum ends, 2 sum ends, 1 plus 2, 2 plus 1, 1 sum end, this is 3. Okay, now for each way of doing this, I have 2 ways of writing 4. So I will add 1 to it, then I will get an ordered composition of 4. So now 2 ways this can be done. 1 plus 1 plus 1 plus 1, just I add a plus 1 there, or I just add this. Just add that 1 to this last sum end. Likewise, this is either I add a 1 like that, or I add that 1 to the last sum end. Here also 2 plus 1 plus 1, and here 2 plus 2. Here I have 3 plus 1 and 4. Okay. And this construction is okay, so you see that these are the 4 expressions where the last sum end is 1, and here you have 4 expressions where the last sum ends are bigger than 1. So therefore, there cannot be anything common between this and this. Okay, because this is, we are having 1 here, we are having something bigger than 1 here. Okay. So in general, this construction works for any n. So in other words, from the 2 power n minus 1 ordered compositions of n, we have 2 sets of ordered compositions of n plus 1. And for each set you see that this composition is reversible. Here I have 1 plus 1 plus 1, so if I just forget this 1, 1, 1, 1, I will get given an ordered composition of 4. If the last sum end is 1, I forget that, and I will get an ordered composition of 3. On the other hand, if the last composition is bigger than 1, I will simply subtract 1 from this. Okay, and I will get an ordered composition of 4 minus 1, that is 3. Okay. So there is a bijection of all ordered compositions of n with this set, and also a bijection of this with this set. Therefore, the total number of ordered composition of n plus 1 is 2 power n minus 1 plus 2 power n minus 1, which is 2 power n. And this is said as 2 power n plus 1 minus 1. Fine. So this proof is by far the most, I would say, complicated proof. So let me see how much time I have already taken. Okay, fine. So I will just do another example and I will stop today's lecture or this lecture. This is once again a very interesting result. So what you are given is a 2 power n by 2 power n chessboard. And let us assume n is greater than or equal to 1. Of course, it makes sense even if I start from n equal to 0. But anyway, let's take n greater than or equal to 1. Now, of course, even if I call it a chessboard, it doesn't matter. The colors of the cells do not matter. They may be all white, they may be all black, but I am simply thinking of a 2 power n by 2 power n grid. Okay, that people call it chessboard. Anyway, that's not an important issue. So, I have something like this for n equal to, let's say 1 or 2. It's a 4 by 4 board. Okay. I have to have another thing. Two by two. What I do, I simply delete or scoop out any arbitrary cell from this 2 power n by 2 power n chessboard. Okay. So remove this. Then, what I want to do, I have given you an infinite supply of this L-shaped objects. Okay, like this. You can definitely rotate it. Okay, so these are called L's. And I think this one, yeah. So you can rotate and, so these are called L's. So given an infinite supply of L's, actually we require exactly that of 4 power n cells minus 1 by 3. L's are given. So the task is to cover this thing, except this is already removed, cover the entire thing using these L-shaped objects, such that the entire board is covered except this removed cell, and these different L's are non-overlapping. Let us see how this can be done. Let us see first an example that this can be done, and then I will give you a general proof. This is an L. I make this L. This is a second L. And that this thing I will include. This is a third L. This is a fourth L. This is a fifth L. Okay, so for this example, it is doable. But why is it in general true? N may be 100, very big chessboard. Still this can be done. Okay. So this again can be proved by induction. Basis n equal to 1. So we have a 2 by 2 board. Now if you remove anything like this cell, you have this L. If you remove this cell, you have this L. If you remove this cell, you have this L. Finally, if you remove this cell, you have this L. So it's a trivial thing. And for the inductive step, what do you do? Assume that this is true for some n greater than or equal to 1. Okay. And then I am given a 2 power n plus 1 by 2 power n plus 1 board. Okay. So this is a 2 power n plus 1 by 2 power n plus 1 board. So what I will do, and somewhere some cell is removed from it. Okay. So what I will do, I will break it down into 4 2 power n by 2 power n sub boards. Okay. So break into 4 2 power n by 2 power n sub boards. Okay. And this removed cell will be either here or here or here or here somewhere, right? Okay. What I will do for a moment, maybe I use a pen of another color. For a moment, I remove this cell, and this cell at the center. Why I am choosing this, because this is here, so I am just choosing the other 3 things. If it is here, I have chosen this, this and this. Okay. If it is here, I have chosen this, this and this. Okay. Since this is here, I am choosing this. And temporarily I am removing this. Okay. Now I have a situation where each of the subboards have 1 cell removed. Right. By induction, therefore, this can be covered by this, actually this minus this, with this cell removed, this can be covered by else. By induction, this can also be covered by else, by induction, this can be covered by else, and finally by induction, this can be covered by else. So only 1 cell is removed. But then if you look at this structure, whatever I have removed, this is another L. So just now put this L. Then your 2 power n plus 1 by 2 power n plus board is again filled with non-overlapping L's. Right? So this is once again a not so trivial example of induction. Okay. So I think I have almost taken 1 hour. Yes. So maybe I stop this lecture at this point of time. So we will continue more with more about induction in the next lecture.